Researchers at Stanford University have recently published a framework called feedback descent. To understand why it matters, we have to look at how reinforcement learning systems currently improve their outputs. Standard frameworks rely on impoverished signals, either scalar rewards or pairwise preference data, which provide at most a single bit of information per comparison. If an AI generates a flawed piece of code, an evaluator knows exactly why it failed, but standard preference learning compresses all that complexity into a simple 0 or 1. The system knows it lost, but the specific reasoning is completely discarded in an information bottleneck. The researchers propose preserving that detailed critique. By capturing structured, natural language feedback, they can provide the model with directional instructions, allowing it to optimize directly in text space. Instead of relying on abstract mathematical scores, language itself acts as high-bandwidth supervision, completely bypassing the limitations of traditional preference learning. When an algorithm searches for an optimal artifact using only function evaluations or binary preferences, it is operating as a zeroth-order method. Without directional guidance, the system guesses. Random searches suffer exponential slowdowns. Proposition 2 formalizes this. An exhaustive search cannot cover high-dimensional space. First-order methods solve this by calculating a gradient vector, taking directed steps directly toward the optimal solution. The core mathematical insight of the paper is outlined in Proposition 1. Textual rationales can approximate this first-order directional information. A binary bit only tells you if an output is better or worse. A text rationale explains exactly how to improve, giving explicit instructions on where to move next in the semantic space. By substituting text rationales for gradients, this approach theoretically enables linear, dimension-free convergence, which effectively bypasses the curse of dimensionality. The entire optimization loop executes strictly at inference time. The system improves its outputs without modifying any underlying model weights. The cycle begins by generating an initial baseline artifact. This is combined with a historical feedback log and fed into a generator model. The generator produces a mutated candidate addressing previous flaws. An evaluator then compares this new iteration directly against the previous best. To ensure monotonic improvement, the evaluator must still output a strict binary preference, confirming whether the candidate is genuinely superior. Alongside the binary choice, the evaluator outputs a detailed textual rationale explaining why the candidate succeeded. This new text rationale is then appended back into the cumulative history block, ready to inform the next iteration. By continually appending accumulated text critiques to the context window, the architecture forms an iterative, self-improving loop that operates completely independently of backpropagation. To test this empirically, the researchers used the creation of SVG visual designs as a proxy for high-dimensional coordinate optimization. Language models struggle to write pristine, complex geometric coordinate math from scratch to render high-quality images. Instead of expecting perfect code on the first try, the evaluator provides precise textual critiques, like pointing out misaligned proportions or flat colors, which guides the subsequent code edits. This chart compares the initial baseline outputs on the left against the refined visuals produced by feedback descent. Looking across the top row, the algorithm adapts the initial unicorn generation to satisfy different aesthetic criteria: inkwash, minimalist, and realistic. The loop refines raw text code based solely on its interpretation of aesthetic rubrics. The rightmost columns contrast the rigid, blocky outputs of arcade pixel art against the strict geometric constraints of stained glass. The results confirm that semantic direction extracted from plain text can reliably and accurately steer high-dimensional mathematical coordinate optimization. The system's utility extends beyond visual artifacts and into raw logic, specifically the challenge of complex prompt engineering. The researchers applied a multi-stage optimization process to datasets that required dense, multi-hop reasoning and precise instruction following. The algorithm dynamically scores candidate prompts against a set of training examples to gauge their effectiveness. In this domain, the evaluator generates feedback that explicitly details exactly which logical constraints the candidate prompt satisfied and which it violated. The exact same algorithmic architecture used to render the SVGs is applied to this prompt logic with zero structural modifications. This proves the framework is completely task-agnostic, capable of operating purely on the underlying semantics of the artifact, regardless of the specific domain. The researchers selected the docstring benchmark for molecule design to act as the ultimate stress test for the framework. This complex application requires collapsing these three-dimensional molecular structures down into one-dimensional text token sequences known as SMILE strings. Feedback descent evaluates these strings using a purely text-based approach, contrasting sharply with specialized, domain-specific graph models like MCTS and reInvent. The chemical evaluations rely on highly specific textual feedback, generating instructions such as the need to decrease specific receptor signaling. The purely text-based iterative loop discovered novel, drug-like molecules that actually outperformed the specialized mathematical graph models. These discovered molecules surpassed the 99.9th percentile of a database containing more than 260,000 compounds. The plotted data reveals Pareto frontier improvements, showing how textual feedback achieves simultaneous, coordinated gains in both docking affinity and overall drug-likeness. Natural language reasoning and critique can effectively replace hard-coded, specialized reward functions. Conversational text critiques are effectively transformed into a universal optimization engine. The future of reinforcement learning requires preserving the high-bandwidth reasoning of human language, rather than compressing our judgments into a single bit of data.